There's nothing like a good cup of coffee in the morning. Some of the people here at the plant like theirs with nothing added. Me, I kind of have a sweet tooth, so I put in a little cream and sugar. Boy, it really hits the spot. Did you know that natural gas can also be sweet? Let me explain. Many reservoirs of natural gas are pure. And by that we mean the gas has a good heating value and is relatively simple to process. It's what we call sweet gas. But in certain regions, the underground natural gas is contaminated. It's what we call sour gas. And we have to clean it up so that only sweet gas is transmitted through the pipelines. This process is called gas sweetening. Now, sweetening your coffee is one thing. Sweetening gas is another. And it's kind of tricky. Instead of adding something to it, sweetening natural gas means taking something out. Now, it's not as easy as this, but it's an important step in gas processing. This is the first section of a two-section module on the principles of amine sweetening. In this section, we'll learn why gas treating is necessary, as well as the basic principles involved in the sweetening process. If a gas forms an acid when it's combined with water, it's called an acid gas. And the most common acid gases found in the petroleum industry are hydrogen sulfide, H2S, and carbon dioxide, CO2. And they occur in a variety of concentrations, depending on the reservoir. H2S and CO2 must be removed from the natural gas because they're corrosive to both equipment and piping. Also, removal of carbon dioxide increases the heating value of the gas being sold and improves pipeline transmission. As we said, sour gas refers to natural gas containing acid gases. Removing acid gases from natural gas leaves you with sweet gas. The process itself is gas sweetening. And that's what's going on here in this section of the plant. The most common process for gas sweetening uses substances known as alkanol amines, more commonly referred to as amines. An amine solution is mainly water, with only 10 to 50% of the solution being amine. Amine solutions absorb acid gases from natural gas, like a sponge. Now, it depends on the concentration of the amine solution, but typically, 1 gallon of amine solution can absorb 3 to 5 cubic feet of acid gas. Before the amine solution absorbs acid gases, the amine solution is referred to as lean amine. After the amine solution absorbs acid gases, it's referred to as rich amine. Now let's talk a little bit about what amines really are. Amines are weak bases which react chemically with acid gases to form salt complexes. Amines are nitrogen hydrocarbon compounds which are categorized as primary, secondary, and tertiary, depending on the number of hydrocarbon groups attached to the nitrogen atom. Hydrocarbon groups will vary depending on the type of amine. Some common examples of hydrocarbon groups are ethanol, glycol, isopropanol, or methyldiethanol. The primary amine, monoethanolamine, has 2 hydrogen atoms and 1 hydrocarbon group attached to the nitrogen, or N atom. Diethanolamine is a secondary amine which has 1 hydrogen atom and 2 hydrocarbon groups attached to the N atom. Tertiary amines include triethanolamine and methyldiethanolamine. Now, they have 3 hydrocarbon groups and no hydrogen atoms attached to the N atom. To keep production costs down and improve the overall efficiency of the system, the amine solution must be recycled. So there are really 2 purposes of an amine sweetening unit. Primarily, it's used to remove acid gases from natural gas before it enters a pipeline. The unit's other purpose is to remove acid gases from the amine solution so that the amine can be used over and over again in the sweetening process. To accomplish these 2 purposes, a number of principles are involved. One of them we mentioned earlier, absorption, is the process by which the amines remove acid gases from the natural gas. Now, acid gases are removed from the amine solution through a process of distillation. sufficient heat must be added to the amine solution to break the bonds between the acid gases and the amines. Amine sweetening also relies on a process called heat transfer. Heat transfer is the process by which heat travels from one substance to another. I'll show you with these two containers, one with hot water and one with cold water. When I bring these two containers in contact with each other, the heat transfer process begins. The temperature of the hot water will decrease, and the temperature of the cold water will increase. The temperature changes are a result of the heat transfer from hot to cold. In amine sweetening, hot and cold amine solutions are brought together in a heat exchanger, and heat transfer is accomplished through conduction. Now, this is necessary because of the narrow temperature range in the sweetening process, and the efficiency of the sweetening process could be adversely affected if fluid temperatures are not controlled within this range. So amines absorb acid gases from natural gas. Then heat is used to distill the acid gases from the amines, with heat transfer as an integral part of the process. Well, that brings us to a stopping point. Take some time to go over this material in your student manual and look at the videotape again if you need to. When you come back, we'll look at the components of a typical amine sweetening unit. Take your time, and I'll see you when you're finished. The process sounds simple enough. Use an amine solution to absorb the acid gases from natural gas, distill the amine solution to remove the acid gases, and recycle the amine solution to start the process all over again. Although the process sounds simple, the system is complex, and as you can see, several pieces of equipment are needed to accomplish the job. This is the second section of the two-section module covering the principles of amine sweetening. In this section, we'll look at the components of a typical amine sweetening unit and follow the flow throughout the amine sweetening process. Typically, the amine sweetening unit is made up of the following components: the inlet separator, contactor column, outlet separator, flash tank, filters, stripper column, reflux condenser, reflux accumulator, reflux pump, reboiler, reclaimer, lean rich heat exchanger, surge tank, circulation pump, and trim cooler. Depending on the type of amine used at your location, your amine sweetening unit may have different components, but the process of amine sweetening will be similar. Let's take a look at the process. Incoming sour gas flows through the inlet separator, where solids and free liquids are removed from the gas. Most of the liquids are separated out by baffles. Near the gas outlet, a mist extractor, sometimes called a mist eliminator, traps liquids entrained in the gas before it leaves the vessel. Some sweetening units also use an outlet separator to remove entrained liquids before the gas goes on to further processing, such as glycol dehydration, or before the gas is sold. From the separator, sour gas flows to a contactor column, where it comes in contact with the lean amine solution. The most common type of contactor column is called a tray column. There are usually 20 trays in the column, with bubble caps on each tray for good liquid-gas contact. The liquid level is maintained on each tray by a weir on the downcomer. The number of trays in the column helps determine the degree of sweetening. Now let's follow the flow through the contactor column. Sour gas enters the bottom of the contactor, preferably at a temperature between 90 and 100 degrees Fahrenheit. While the sour gas rises through the bubble caps on each tray, lean amine enters from the top of the column and flows downward. In order to prevent hydrocarbon condensation, the temperature of the lean amine should be kept 10 degrees warmer than the sour gas temperature. As the gas rises through the amine, it disperses in the form of bubbles and forms a froth. Natural gas then disengages from the froth, flows through the vapor space, and up through the liquid on the next tray. Meanwhile, the entrained amine solution in the froth falls back onto the tray, then flows through the downcomer to the next tray. It's important to note that almost all the absorption of acid gas takes place on the trays rather than in the vapor space between the trays. A mist extractor at the top of the contactor traps entrained liquids from the gas before it enters the gas outlet. The liquid then drops back onto the top tray and rejoins the amine stream. Sweet gas leaves the top of the contactor to be sold or further processed. And at the base of the contactor, rich amine solution containing acid gases is discharged. Another kind of contactor column is called a packed column. In a packed column, the surface area within the vessel is increased by filling it with a packing material. The amine solution coats the packing material for a good contact surface between the amine solution and sour gas. Now, before we go on to the next vessel in the process, we need to understand the term flashing. Operating pressures change as the solution flows through the sweetening unit. For instance, the contactor column operates at elevated pressures, usually in the range of 200 to 1,000 psig. Now, from the contactor column, the rich amine solution flows to a flash tank, which operates at much lower pressure. Now, this drop in pressure causes gas in the amine solution to escape, or flash. And it's very similar to what happens when you open a bottle of carbonated soft drink. Liquid inside the bottle is under pressure, while all around the bottle is atmospheric pressure. When you unscrew the cap, pressure quickly escapes from the bottle. Bubbles of carbon dioxide flash. And not only can you see the bubbles, but you can also hear the flash. And once again, the process is called flashing. Now, that's what takes place in the flash tank. Pressure in the flash tank should be low enough to flash the acid gases, but high enough to maintain a constant amine flow to the stripper column. Vapors in the flash tank are usually sour and are either recycled to the contactor column or flared. A liquid layer on top of the amine solution may be formed by hydrocarbons entrained in the amine solution. The liquid layer is skimmed off, and the rich amine is drawn from the bottom of the tank. After leaving the flash tank, solid matter and any remaining entrained hydrocarbons must be removed from the amine solution for proper operation. Now, filtering can be done in several ways. One way is downstream of the flash tank and upstream from the lean-rich heat exchanger. Now, filtering at this point usually involves mechanical filters to remove solid matter and an activated carbon filter to remove entrained hydrocarbons. Filtering can also be done before the lean amine stream enters the contactor. For good solution control, solid matter down to the 10 to 15 micron size should be removed. Some sweetening units will have filters on both the rich and lean amine streams. After filtering, the next step in the process is the lean-rich heat exchanger. Now, this heat exchanger is usually a shell and tube type, and due to the corrosiveness of H2S and CO2, the tubes are usually made of stainless steel. The rich amine stream is heated to approximately 190 degrees Fahrenheit by the lean amine before flowing to the stripper column. The stripper column is sometimes called a regenerator because within this vessel, acid gases are removed from the rich amine, resulting in or regenerating lean amine. Now, this vessel is either a tray column or packed column and operates near atmospheric pressure. The rich amine solution, preheated in the heat exchanger, enters the top of the stripper column and flows downward. The rich amine solution is further heated by incoming steam from the reboiler, flowing upward from the bottom of the stripper column. The heat from the steam helps strip the acid gases from the amine solution. The steam also helps sweep the liberated acid gases out of the stripper column. Next in the process is a loop made up of the reflux condenser, reflux accumulator, and reflux pump. Overhead vapors from the stripper column, mostly water vapor and acid gases, pass through the reflux condenser, where water vapor is condensed into liquid water. In this way, water and the small amount of amine which may have vaporized in the stripper column are recovered. Water and acid gases from the reflux condenser then flow to a reflux accumulator, where water is separated from acid gases. A reflux pump returns the water back to the stripper column for reflux. Depending on the amount of H2S present, acid gases from the accumulator may be sent either to a flare stack or to a sulfur recovery plant. After leaving the stripper column, the lean amine solution goes to the reboiler. The reboiler, used to create steam for the stripper, is usually a direct-fired heater. In gas treating facilities, this method of heating consists of controlled combustion inside an expandable tube surrounded by boiling amine solution. The heat medium could also be steam or hot oil if available in sufficient quantity. The next step in the process is the lean-rich heat exchanger. From the reboiler, the hot lean amine flows through the heat exchanger and is cooled to a desired storage temperature by the rich amine solution on its way to the stripper column. The cooled lean amine from the heat exchanger is kept in a surge tank until it's pumped back to the top of the contactor column to begin the cycle again. Periodically, water and amine are added to the surge tank to make up for losses of these two liquids during the process. Another vessel in the process is the reclaimer, a vessel that is not always used in a sweetening unit, but when it is used, the reclaimer can greatly reduce operating problems. A small portion, usually 1 to 3%, of the lean amine solution from the stripper column is semi-continuously fed to the reclaimer and boiled. The distilled, pure lean amine is returned to the main solution, leaving behind contaminants such as hydrocarbons, heat-stable salts, and solids. Whether a reclaimer is used or not, contaminants should never exceed 1% by weight in the circulating amine solution. As contaminants accumulate in the reclaimer, liquid temperature rises until it reaches a set point which stops operation. At that point, the reclaimer must be drained of the accumulated solids and then put back in service. As we mentioned earlier, the lean amine solution in the contactor column must be hotter than the sour gas being treated. But at the same time, high amine temperature can reduce the efficiency of acid gas removal. Now this component, called a trim cooler, helps solve that problem. A trim cooler is used to lower the temperature of the lean amine solution coming from the surge tank and control the temperature of the lean amine solution going to the contactor column. The contactor column. That's where the process starts all over again. Sour gas enters the bottom of the contactor column, while recycled amine solution flows down from the top. Recycling the amine solution is a key point of the sweetening process, and in fact, the main purpose for most of the equipment in an amine sweetening unit. Well, that brings us to a stopping point. Now it's time to look over this material in your student manual and answer the questions. This also brings us to the end of this module. If you have any questions, consult your student manual or look at the videotape again. Amine sweetening is a good example of how a number of principles work together, with the result being efficient operation and a quality product. Remember that your understanding of the principles of amine sweetening helps maintain that efficiency, helps keep product quality high, and helps generate revenue for our company. Good luck, and I'll see you next time.